So while I look at representing covalent bonds in a number of, or in one particular way, I'm going to use the stick method, but more technically we can describe it as Lewis diagrams. Now Lewis diagrams tend to show all outer shell electrons in all of the atoms, but you can represent those electrons as dots or crosses, or electron pairs in, for example, covalent bonds, as sticks. So let's take carbon as our example here. Now carbon, of course, normally in its isolated form has 4 electrons in its outermost shell, like that. Therefore needs 4 extra electrons to complete its octet. And it can get those 4 extra electrons by forming 4 covalent bonds. It will share each of those electrons with another, forming 1 covalent bond each. So there we're going to need 4 covalent bonds. Now remember that in this particular case I'm A, generalizing very much, and B, I'm not considering charged atoms, and I'm not considering dative covalent bonds. So this is looking at it very basically. But if we just say, okay then, if we're not talking about dative covalent bonds, and if we're not talking about charged atoms, I mean we'll talk about these a little bit later, essentially we're going to form 4 covalent bonds, and I'll show those as sticks like that. Now that's one possible combination for our covalent bonds. These are 4 single covalent bonds that we have here. But there are other possibilities as well. We could, for example, have our 4 covalent bonds as 2 single and 1 double. There are other possibilities as well. We could have 2 double covalent bonds, or 1 single, 1 triple. Now remember what each of these lines or sticks represents. It represents a pair of electrons, 1 electron from carbon and 1 electron from the other atom. So we can say each carbon has 1, 2, 3, 4 of its own electrons. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and when sharing with another it will form 2, 4, 6, 8 complete octet, 2, 4, 6, 8 complete octet, 2, 4, 6, 8 complete octet, 2, 4, 6, 8 complete octet. Sorry about all the noise. Now oxygen has 6 electrons in its outermost. And we can represent those electrons around the oxygen by putting 1, 2, 3, 4, and then I will pair up to give 6 electrons like that. To get to noble gas electron configuration, now I'm generalizing and simplifying here of course, but it works reasonably well for period 2 elements. Here we have 6 electrons. To get to noble gas electron configuration, it needs 2 extra electrons needed, and therefore to form 2 covalent bonds. So in other words, what we'll do is each of these electrons here is going to share another electron with another atom, and that therefore forms our 2 covalent bonds, 2 possible covalent bonds for oxygen like that. But again, there is another alternative. We could have, instead of two single bonds, we could have one double bond. Remember, each stick represents a pair of electrons, one from one atom and one from the other atom that I'm not showing here. So nitrogen, which is in group 5 or group 15 depending upon where you are, has 5 electrons in its outermost shell. So here's nitrogen, 1, 2, 3, 4, and I'll pair that one up, 5. It needs an extra 3 electrons to get to noble gas electron configuration, and by sharing 3 of its electrons in forming covalent bonds, it can complete its octet, and we can have a number of combinations again. You'll notice here one lone pair of electrons that's not used in the bonding, and each of the other electrons are used in a covalent bond. Each stick represents a pair of electrons, one of which is nitrogen's and one of which is the other atom. So another possibility, we could have double and one single, like that, or, as I almost said, one triple bond, like that. And notice in each case of 8 electrons, 1, 2, 3, 4, 5, and another one, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And the number of electrons for nitrogen is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Each stick representing a pair of electrons, but only one of those electrons is from nitrogen.